Course, PHM, Prognostics Health Management. Topic: Optimal Maintenance of Industrial Asset Networks. Session 4. Optimal Component Maintenance, and Optimal Maintenance of the Asset Network. Cases: truck fleet, hydraulic power plants, ships fleet in dry docking, solar farms, and wind turbines. The material used in this video can be found in the book in Spanish Optimización del Mantenimiento de Activos Industriales, in English, Optimization of Industrial Asset Maintenance. Those interested can request the book from Hi. Holistic Maintenance. Session 4 Part 4.1. The holistic maintenance process involves an integrated view of the two problems that must be faced. Starting from the study of the behavior of each component that may fail in an industrial system, to reaching the decision-making on what should be done with each asset in the short or medium term. This implies that two types of models must be combined: predictive analytics and prescriptive analytics. The image presents asset network, wind farm industrial assets, wind turbines components. These are the result of the hierarchical decomposition of the asset into parts, up to the basic components. An industrial asset can be conceived as composed of systems, each of which can be composed of a set of subsystems, each of which can be composed of a set of components, corresponding to the last level of the hierarchical tree, and which, normally, corresponds to the site where the failure that affects all the elements of the branch of the hierarchical structure occurs. This allows you to establish a hierarchical structure, which describes the entire asset based on the integration of components. As an example, we present how a wind turbine could be visualized. Asset maintenance integrated by multiple components. When this type of asset fails, it can happen, full shutdown, if a component or group of components fails, or duration, loss of productivity due to the failure of a component, but the integrated asset remains operational. The goal of comprehensive mathematical modeling is to determine the optimal policies for the operation of the assets, taking as a reference that they are composed of multi-level fault structures, each of them with its own probabilistic characteristics of failures of its components. The key decisions are as follows: optimal consumption of the asset before its next maintenance, and maintenance actions to be carried out, once the decision has been made to stop the asset to carry out maintenance work. The Failure Probability Model, FPM, is a predictive analysis model, intended to determine the parameters that define the individual failure probability of each asset. For mathematical modeling purposes, assets are represented by a multi-level hierarchical structure, which at the top level corresponds to a sum of elements. The image presents as an example, the hierarchical decomposition of an industrial forklift. The Failure Probability Model, FPM, is a predictive analysis model, intended to determine the parameters that define the individual failure probability of each asset. For mathematical modeling purposes, assets are represented by a multi-level hierarchical structure, which at the top level corresponds to a sum of elements. The image presents as an example, the hierarchical decomposition of an industrial truck. To assign maintenance activities and production activities, analytical models are used. Prescriptive optimization, aimed at determining optimal decisions, based on mathematical programming, and predictive forecasting, aimed at determining the operating conditions of the equipment, models using artificial neural networks, machine learning, and advanced statistics, to determine the information related to the failure of each equipment. The hierarchy of decisions differentiates them as strategies, tactics, and operations. Typically, they are referred to as planning, refers to long or medium-term decisions, in which the major maintenance of industrial facilities, or their large parts, is defined as a whole, and scheduling, corresponds to short-term and real-time operation. Define and detail the activities that are required to perform maintenance on parts, machines, and vehicles. The first step in addressing decision-making is to define the architecture and the operation of the decision support system, which must integrate the mathematical models that are required to solve the real problem of the company, which is to maximize its economic productivity. The architecture can be as simple as the entire system running on a personal computer or running in a distributed manner in a client-server environment. The current state of computing involves the integration of edge computing and cloud computing to implement highly complex mathematical models. The model aims to schedule maintenance in such a way as to minimize costs or maximize revenues, resulting from the simultaneous coordination of production and maintenance activities. Optimization is carried out considering, among others, the following aspects: the demands satisfied by the production chain, maintenance costs, the usefulness of production, the resources used in maintenance processes and their availability. The constraints included in the models simulate each production line in a customized way. The mathematical models needed to carry out this work can be classified into two types: models to optimize decision-making in maintenance activities, and support models for general maintenance management activities, integrated with models for the optimization of production activities. The models normally required are maintenance of the production plants, including the process units that make up the large industrial facilities. These processes may involve the closure of plants or units, or the reduction of production leading to a decrease in the productivity of the industrial asset. Asset maintenance, associated with the maintenance of multiple assets operating in an industrial environment, which require maintenance activities as the productive life between maintenance is consumed. These maintenances are scheduled at the team level, each of them independently. Inventory management of spare parts and spare parts. Normally, to ensure the timely maintenance of spare parts, it is necessary to maintain inventories of spare parts and spare parts that are associated with working capital that generate high financial costs, and scheduling of activities in industrial workshops. Industrial workshops are an integral part of factories and have the function of ensuring maintenance activities. To visualize the architecture that will soon be typical, the case of PHM functions in the bogies of a high-speed train is presented. The architecture includes edge computing, distributed processing of PHM functions in train bogies, and cloud computing, centralized processing, on a high-performance computer on the train, or outside the train, to consolidate information from all bogies. The bogie is the most important and complex part of a train's network of rolling stock components. It is responsible for fundamental functions such as body support, transfer of braking and traction forces, train stability at high speeds, safe passage of the rail curve and good and comfortable driving. Today, the bogies of a modern train are made in one piece, equipped with computing power and artificial intelligence. Connectivity of mathematical models for maintenance optimization. Hopefully, the starting point will be linked to an asset management system, AMS. AMS is an IT product that already existed in organizations prior to Digital Transformation 4.0, and they contain the basic information needed to implement the system to support asset maintenance decisions. The AMS, along with the ERP, can provide information that will be used as input information for the decision support system. The first linked model is DEM, Demand for Maintenance Services, Historical Information, and Committed Services. For example, comprehensive maintenance contracts signed with third parties. They are also expected to provide the information on the useful life of the assets, asset resume. Historical information of the events that occurred to the assets. This information is critical to prescriptive analytics models. The optimization model INV provides inventory policies for spare parts. The basic information of this model should be the resume of the industrial assets, which should store the history of the maintenance services and the resources used. The first predictive analytics model to be developed is related to the PHM function. The PHM model must run, theoretically permanently, for each component that is in operation. The functions of this model are: anomaly detection, defines whether a fault occurred and, if possible, classifies the fault specifically. Level of degradation of the asset, determines the loss of useful life that the asset has suffered. Forecasting, determination of the expected useful life until the next failure, a parameter known as rule, remaining useful life. This parameter should be characterized by a probability distribution function. The probabilistic characterization of the rule will be used to generate synthetic random scenarios, which can be used to formulate stochastic optimization models for decision-making. The information from the PHM model is processed in the stochastic optimization of individual maintenance, IMO, aimed at the individual analysis of asset maintenance. If the PHM model has produced information at the level of the asset's components, the hierarchical tree is required as input for a holistic view of the integrated asset. The main results of the IMO model are ideal consumption of the service life dimension until the next maintenance, and activities to be carried out in the next maintenance. IMO can be run in two versions. IMO-T that produces the information for the SAND-OP, production activity planning, model, and IMO-O that produces information for the MOS model, planning activities in the workshop. The functions of IMO-T are described below. The IMO-T model is fundamental for the synthesis of the PHM information for processing in the SAND-OP model. SAND-OP should receive as input the list of assets that can be used during the planning period. From a maintenance standpoint, the SAND-OP model produces the functions that each asset must fulfill, including the times in which it must undergo maintenance. That is, for each of the periods of the planning horizon, divide the assets into two groups, those that will be operational and those that need to be serviced. To do this, associated with each asset, the cost curve of deviation from the optimal consumption policy of the useful life dimension of the asset must be received. These costs must be included in the target function, so that the SAND-OP model selects decisions that maximize the firm's economic utility. The image presents the summary of the steps involved in the holistic planning of the maintenance process, which can be summarized in 6 steps. First, PHM model determines the condition of the asset and/or its components. Model based on predictive analytics. The following models are optimization models based on prescriptive analytics. Secondly, the IMO-T model, it performs the individual optimization of the optimal maintenance of each asset, ignoring the existence of other assets. Thirdly, the SAND-OP model performs integrated planning of asset production and maintenance activities. It involves a holistic view of the industrial system. Fourthly, the IMO-O model determines in detail the maintenance activities to be carried out in the workshop for the assets that are going to go into maintenance. This applies to both planned maintenance and corrective maintenance. Fifthly, the SCH model produces the scheduling of production activities and is outside the maintenance environment. Sixthly, the MOS model produces a detailed scheduling of maintenance activities in the workshop. For practical purposes, the hierarchical tree is the way to relating maintenance activities in the MOS model, and the demand for spare parts in the INV model. Analysis of the maintenance of individual assets. Session 4 Part 4.2. The IMO model analyzes the information produced by the PHM model, from the point of view of optimizing the maintenance of the asset, without considering that it is part of a network of assets that must operate synchronously. It is proposed to be a non-anticipatory stochastic optimization model, also called scenario optimization. This characteristic is due to the volatility associated with the rule, remaining useful life, which determines the risks associated with decisions about when to perform maintenance. It is assumed that the asset consumes the rule in a dimension that depends on the asset. For example, for vehicles it can be kilometers traveled, for generation plants megawatts, for production lines tons processed, for certain materials the time elapsed since the beginning of their use. For a specific asset, there could be more than one dimension of rule consumption, with the equipment failing under the condition, first come, first served. In the stochastic optimization model, for the case of maintenance of individual components, the results will be consumption of the service life dimension until the next shutdown, and maintenance activities to be carried out, associated with the optimal consumption of the useful life dimension. Internally, the model must optimize a utility function, and control operational and financial risk management. The presentation considers a basic case, in which the only random parameter is the rule, the time to the next failure. For each asset, the scenario tree will be several series of rules, that can occur until the next maintenance. For the first failure, you have an rule 0 that is conditioned by the current state of the system. This value is the result of the PHM model. For remaining failures, it should be noted that the time to the next failure may depend on the type of maintenance performed on the asset. In this case, there is only one type of maintenance, for example, changing the used asset to a new one. This data would be the result of the technical specifications given by the manufacturer. As part of the results of the PHM model, the probability distribution function of rule 0 is obtained, from which multiple synthetic scenarios of asset, or component, failure can be generated.
El árbol de escenarios implica múltiples tiempos de falla diferentes para la primera falla. Como se considera una sola política de mantenimiento, reemplazar el activo, a partir de la primera falla, el tiempo entre fallas podría ser el mismo, si se asume el dato del fabricante como cierto y determinístico.
The important decision, the one in the here and now, is when the next maintenance should be carried out, a decision that has to be independent of the scenarios. Prior to the optimization process, a range can be established in which maintenance should be performed. The range will be defined between the minimum and maximum time until the next failure. If the decision maker decides based on one of two simple criteria, the selection of the minimum value is typical of a conservative and risk-averse policy. In the end, the asset certainly won't fail, but the asset's lifespan is lost. But, if the decision maker selects the maximum, it implies a risk-prone position. In the end, it is certain that the asset will fail, and the full cost of the asset's failure will be assumed. Which is the best decision is not intuitive. Rational is a decision that implies that the first maintenance is done somewhere in the middle of the range. There will be potential scenarios in which the useful life of the asset is lost, and the opportunity cost is paid for not using it. And there will be potential scenarios where the asset, or component, fails and the cost of failure is paid. The decision of what is best depends on the value of the costs associated with the maintenance and failure of the asset. If the manufacturer's data is considered random, the future times between failures must be the result of a synthetic failure time generation process. If there are multiple maintenance options, such as replace or repair, failure times must be generated for each maintenance policy, and it would be the mathematical model that, when selecting the maintenance policy, implicitly selects the time to the next failure. This is the function of the mathematical model for complex cases, typical of real industrial systems. When all assets are considered simultaneously, maintenance may not be possible on the so-called ideal date. This can be due to multiple reasons. For example, not all the necessary resources are available at any given time, that is, for reasons of technical feasibility. It is necessary to adjust the dates in order to be able to produce the demand for final products, which must be met by the industrial system, for example, for reasons of installed capacity, and it is advisable for economic reasons to adjust the dates. For example, moving maintenance from working days to non-working days, or vice versa. As the number of assets increases, the complexity of the math problem increases. To introduce the concept, let's consider the case of two assets that have the same ideal date, but for technical reasons, the two assets cannot be held in the same period. In this case, at least one of the two assets will have to adjust its maintenance date, delaying or bringing forward the ideal date. The action to be taken will come at a cost, depending on the decision. It will be the cost of the risk assumed, if it is delayed, and it will be the opportunity cost for loss of useful life, if it is brought forward. In a mathematical model, the process to follow might be: include a binary variable that is equal to 1, if the maintenance of asset A is performed during period t. We will call this variable man with subscripts a and t. In addition, a restriction must be introduced that limits the maximum number of maintenance to be performed during a period. This is expressed as the sum of all assets A, of the man variable must be less than, or equal to, the maximum number of maintenances, for any period. In this case, the maximum number of maintenances is equal to 1. While it is possible to use the above mathematical model to coordinate all assets, the combinatorics that are generated by increasing the number of assets, and the number of periods, can make the problem very complicated to solve in reasonable times. For this reason, another approach based on finding the differential costs, which are assumed by diverting the maintenance of the asset from its ideal date, is analyzed. If this is done for all assets, it is possible to implement faster mathematical models. The process involves extending the EMO model so that it produces a curve of additional cost due to the deviation of the maintenance date from the ideal date. This information will then be incorporated into the SANDOP model, which will simultaneously optimize industrial production and asset maintenance. The figure shows the utility function of the operation of the individual asset, which is maximized on the ideal date for the maintenance shutdown. Any deviation from the ideal date must imply loss of profits, otherwise the ideal date would not be the optimal date, defined as one that minimizes costs or maximizes the utility of the asset's operation. If the maintenance date is brought forward, the loss is generated by not using the asset at its maximum capacity, or operational productivity. For example, if an engine that can ideally travel 6,000 kilometers before an oil change has its oil changed after 5,000 kilometers, it will have lost the opportunity to travel an additional 1,000 kilometers, which implies a loss of oil life. The greater the anticipation, the greater the loss of opportunities. On the other hand, if the maintenance date is postponed, the probability of failure of the asset, or component, will increase, which implies taking greater risks, and therefore assuming a higher risk premium. To construct the additional cost curve, the range of variation of the first maintenance date is known. The utility curve of the maintenance date makes sense for that range. Outside that range its value would tend to minus infinity, or its cost to infinity. By knowing the range of variation on the first maintenance date, it is possible to assess the cost, or utility, of holding the asset individually for any maintenance date within that range. To do this, you must set the result date of first maintenance equal to the date for which you want to evaluate the cost or utility of maintenance. This is achieved by introducing a constraint into the model that sets this date. In general, a continuous curve over the entire range of variation is required. This curve can be achieved by evaluating the curve at all points in the interval, which is not feasible for a continuous interval. What can be done is to evaluate a discretized curve in the interval of variation, using several points within that interval. The accuracy of the curve, and the computational cost of evaluating it, will depend on the number of points. This aspect depends on the mathematical modeler, and the experts in the production and maintenance problems. The expected maintenance cost is equal to minus the utility. Several points are determined to cover the range of variation, which are evenly distributed, and the function at these points is evaluated. With this information, a linear curve is constructed that approximates the required continuous function. And the evaluation of the maintenance cost function at each of the selected points within the range of variation. It must be clear that the minimum maintenance cost is a sunk cost from the point of view of production, that is, there is no production plan that can alter it. For this reason, its variations are additional costs, resulting from the impact on production plans, with respect to the ideal date. An algorithm for constructing the additional cost curve is presented in the image. The connectivity of the EMO-T model with the SANDOP model must be completed, including the additional cost function as part of the objective function of the SANDOP. The image presents a possible formulation. It should be noted that, by means of the additional cost curve, the probabilistic aspects of maintenance are synthesized. Therefore, the SANDOP model may be a deterministic model, which with respect to maintenance has endogenized the volatility of maintenance, by means of the additional cost curve. Maintenance of industrial asset networks. Session 4 Part 4.3. Case, Maintenance in electricity generating companies. Holistic maintenance consists of two stages. In the first stage, PHM models must be implemented for all assets that make up the asset network of the industrial system. In the second stage, an integrated asset network optimization process should be implemented. These two stages can each be made up of multiple models that fulfill specific functions, and that together become the artificial hypothalamus of the maintenance system, which in turn is a part of the artificial brain of the organization. With respect to conventional modeling of the operational planning of an electricity generation system, maintenance modeling involves converting the availabilities of generation units, of any type, into variables derived from decisions associated with maintenance. Constraints that modeling must account for include resource consumption, and the time windows in which maintenance must be performed. Optimization aims to schedule maintenance in such a way that revenue is maximized. For this should consider energy committed in the long-term market, price predictions in the spot market, firm energy allocated or sold, and any charges that affect the generator's revenue or expenditure. The results of the PHM model as it relates to the rule, remaining useful life. To assign maintenance activities to one or the other period, the production capacity of the periods in which maintenance is performed is reduced according to the magnitude of maintenance. This loss of capacity can be total, if it involves a shutdown of the industrial asset, or partial, if it involves partial shutdowns, or loss of generating power due to maintenance activities. In the case of oligopolistic markets, such as the electricity market, the greatest complexity that is expected to model maintenance decisions is the relationship between short-term marginal costs, the reference for the value of energy in the spot market, and maintenance, since the maintenance decisions of the dominant agents, price makers may produce an increase in marginal cost for reasons of lower system-wide availability. However, for most pricing agents, due to the size of their generation system, maintenance at their plants is not expected to alter spot market prices, with the exception of the agent that is setting the price. The concept of modeling is based on the use of two coordinate models. Dispatch model, which provides the value of marginal costs, as a proxy for spot prices, which are used in the maintenance optimization model, which evaluates the expected revenue derived from maintenance decisions. In the case of price makers' agents, these two models can be joined into one, using mathematical programming with equilibrium constraints, MPEC. The image presents what could be the decision support system of a generator, which follows the principles of enterprise-wide optimization, whose architecture is conceived as composed of 9 models, which are described below. The diagram only includes 8 models. 4 functional models are required, associated with the industrial activities of the generator. These models are SCD, Robust Supply Chain Design. It supports the design of the network of assets that make up the industrial generator system. Optimo, Maintenance Optimization. Aimed at producing the planning, and scheduling, of maintenance activities in the generator asset network. ETRM, Energy Trading and Risk Management. It supports the marketing of energy, mainly electricity, which is handled by the agent, and UC, Unit Commitment, Real-Time Dispatch of Generation Units. All these models are stochastic optimization. In this presentation, a possible implementation for the Optimo model is discussed. 4 functional models provide preprocessed input data to the prescriptive models. Predictive models are based on artificial neural networks, machine learning, and advanced probabilistic models. The predictive models are PHM, Prognostic and Health Management, provide parameters for the Optimo model. Jensen, Monte Carlo Synthetic Generation. Models required for the generation of scenario trees of stochastic optimization models. Kalman, State Estimation via Kalman Filter. They predict short-term random variables in the decision-making environment, and Spot, Arima-Garch statistical models for short-term prediction of spot prices. The image shows the connectivity between predictive and prescriptive models. Another support model is needed to know the behavior of the electricity system and its market, that is the expected dispatch of the plants and the spot prices. Therefore, the generating agent requires a simulation model of the dispatch of the interconnected system. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by Optex, the optimization expert system, the generative artificial intelligence of high, using the models that traditionally make up a decision support system. Real case, maintenance of hydroelectric chain. The dynamics of the process are associated with a state transition model, operational, under maintenance, in which the element is considered to have a maximum operational useful life, PM20, and that during this time maintenance must be carried out with a fixed duration DM20. In an MSP approach, the value of PM20 corresponds to the rule. At the beginning of the planning period, each item has a remaining run time, PR20, which depends on the last maintenance performed, and therefore the first maintenance must be performed during an initial period with a predetermined duration. The decisions that the model must simulate are related to the dates or periods, phi x2x, when each maintenance starts, a decision that generates periods of unavailability of the element that is under maintenance, which is simulated by the dixdx variable. Maintenance is not supposed to be interruptible. A single type of maintenance is considered, but several types can be considered. In general, the model should be aligned with the company's maintenance practices. On the other hand, it is considered that there are limited resources to perform maintenance, which guarantees that the amount of resources consumed respects the inventory of existing resources. For this, it is required to know the amount of resource consumed per maintenance period. Examples of types of resources are types of labor, machinery, spare parts, etc. The objective of the modeling is to determine the impact on productive capacity derived from maintenance decisions, which is different for each element, and can be the result of the interaction of several maintenance decisions. This is due to the relationships between the different elements, and the possibility of consumption of common resources in maintenance processes. The result of the modeling is a detailed maintenance plan for each period of the planning horizon. From the point of view of time, an adequate modeling allows the scalability of the model in such a way that with the same algebraic model decisions are made for the medium and short term, and with slight adjustments for programming of operations. A deterministic model would be based on a single scenario tree for random variables. Random variables can be associated with multiple dimensions of uncertainty, for example, hydroclimatic variables, that is the availability of renewable energy sources, spot price of electricity, electricity demand, and period of failure of assets. This aspect needs to be very flexible, as it represents the random environment of decision-making. For example, a stochastic optimization model that only considers hydroclimatic variables as a source of uncertainty may be very useful in the short or medium term. However, in the long run, when what determines the future is more tied to economic variables, for example, the price of oil, the growth of the economy, etc., it may be of little use. Ideally, the variables to be included in the random scenarios can be configured by the user. For this model, it is proposed to use a two-stage scenario tree. The first stage is related to the here and now, and is associated with decisions about the next maintenance of each asset. The second stage, which multiplies as more scenarios are considered, is related to the simulation of operations of what may happen after the first maintenance. Decisions in this dynamic systems imply that the total cost function corresponds to the sum of two functions. The current cost, which is due to decisions in the here and now, is conventionally assumed to be deterministic, which is not always true. Plus, the future cost, which occurs because of decisions made in the here and now. It corresponds to a random variable whose value is unknown, and it is a matter of probabilistically characterizing it using the mathematical model. Next, the application of the Optimo model to an energy production system is presented, which combines hydroelectric generation plants, reservoirs and storage ponds. The loss of profit due to the paralysis, or the collapse, of the production system must be considered, considering that the price of electricity varies hour by hour, day by day and month by month. The constraints associated with the limited resources available to perform maintenance must be considered, ensuring that the amount of resources consumed is respected, according to the inventory of existing resources, for example, specialized professional personnel, work crews, time, equipment, vehicles, spare parts. The impact on production capacity derived from maintenance must be determined, which is different for each element. Generation units, the effect is summarized in the total or partial unavailability of the generation unit that goes into maintenance, and tanks, the effect is summarized in the loss of the capacity to store water resources during the period of maintenance. Additionally, there may be interaction between the maintenance of elements of different types. This is due to the relationships between the different elements, and the possibility of common resource consumption in maintenance processes. For example, to coordinate the maintenance of a tank, it is necessary to shut down the tank-dependent generation units. The following figures present the results of a real-life case scenario. In these results, it is possible to visualize the coordination of the maintenance of a tank, and the respective generation unit, that uses the water regulated by the tank. Green, in operation. Blue, start of maintenance, and red, under maintenance. Below are the algebraic elements that are part of the maintenance model of power generation systems. Index is M reservoir on generating unit RM maintenance resource T period Q period. Decision variables. CUG T ineffective generation capacity in the period diet, M unavailability of reservoir under maintenance due T on unit unavailability due to maintenance Phi TM binary variable indicating active reservoir maintenance period FAU T on binary variable indicating non-active unit maintenance period Phi TM binary variable maintenance start period. Reservoir FIU T on binary variable maintenance start period. Hydraulic unit VART M artificial variable resources. Realistic case, asset maintenance in interconnected systems. Holistic planning is understood as the integrated planning of the largest installations of the electricity system. These can be power plants and/or generation units, energy storages, conduction channels, reservoirs, transmission lines, and transmission system substations. To analyze the above, a model can be generated that integrates the economic dispatch, or any modification thereof, with the maintenance model, equations that represent the maintenance process for each type of installation. The objective of the operation will be to maximize the social surplus, which for electricity systems in which inelastic demand is assumed, corresponds to minimizing operating costs. Below are the results of the realistic example case. In these results, it is possible to visualize the coordination of the maintenance of the largest generation plants of the SIN, in Colombia. Below are the results of a realistic case study. In these results, it is possible to visualize the coordination of the maintenance of the larger generation plants of the Colombian interconnected system. As a result of the optimization model, the figure shows the availability of the generation plants, for each period of the planning horizon. The figure shows the generation of hydroelectric power plants for each period of the planning horizon. Maintenance coordination of competitive generating agents. This model can be used by a generator with dominant power, price fixer, who wants to establish the periods in which it is most convenient to carry out its maintenance, in order to maximize its income by affecting the spot price. If the generator has market power, it should use a mathematical programming with equilibrium constraints, MPEC, model. Real case, maintenance of a network of solar power plants. The availability of energy and demand introduce many uncertainties into the operation of low-carbon power grids. One way to address such uncertainties in network operation is to develop an accurate forecasting algorithm. Subject areas in supply-demand modeling in solar farms include availability of renewable source, wind and solar, demand forecasting and demand pooling, rule of assets, solar cell groups. All these issues are not dealt with in detail in this document, but it should be noted that they are part of the problem and that, if all of them are not resolved, the decisions that are made do not have to be optimally complied with and may lead to undesirable consequences. Below is an example of how AI can be leveraged to solve photovoltaic prediction tasks following the model proposed by Yang et al. To predict solar irradiance on a farm during the K+1 period. The figure shows the geographic locations of the target solar farm, C6, and N neighboring solar farms. To forecast solar irradiance, Yang et al. Formulate an autoregressive model, R, with exogenous input, ARX, where xk solar irradiance on the target solar farm in period K, yk solar irradiance in the solar farm I in the period K, QK prediction error in the period K, F, ARX function, and N, DYME user-defined integer parameters. The formulation implies that the solar irradiance in the next period, xk plus 1, on the target solar farm depends not only on the local solar irradiance, but also on the solar irradiance on neighboring farms. Studies based on real-world renewable energy data, in California and Colorado, suggest that this ARX model is suitable for photovoltaic energy forecasting, PV, over the next 1 to 2 hours. Moderacy et al. Propose a scenario-based approach that facilitates the potential of data to incorporate the uncertainties of renewables. Suppose there are H historical scenarios D equals D1, D2, DH, which is a subset of all possible scenarios D. In each historical scenario Dn, the net load forecast errors on each bus are logged. The Optimo problem is of the stochastic optimization type and determines the optimal economic dispatch considering maintenance. It is formulated as presented in the image, where θH represents the probability associated with scenario H, the vector pH represents the power generation by all generators, at all intervals during the planning horizon, if scenario H occurs, and μ represents the maintenance decisions, which affect the generation capacity, and the rule of all components. The vector ch captures the cost coefficients associated with generators. G1 less than or equal to 0 represents scenario-independent constraints, such as ramp and generator capacity limitations, and G2 less than or equal to 0 represents the scenario-dependent constraints, such as generational load balancing constraints. Real case, COT fleet dry docking, maintenance scheduling model. A classification society is an organization that conducts regular inspections on service ships to ensure that ships comply with a set of standards. This criterion can be measured by the company satisfaction indicator and the classification certificates indicator. Classification society satisfaction can be measured in terms of the number of surveys conducted and the number of pending surveys. The classification society certificates indicator is measured based on the due dates and expiry dates of the surveys. Dry docking maintenance scheduling. Efficient scheduling of dry docked ship maintenance is a vital component in the overall strategic management of a merchant ship fleet. When this process is scientifically managed, significant revenue and efficiency gains can be realized, as downtime is minimized. Normally, ships are scheduled to undergo maintenance at a shipyard every 2.5 years, for an interim classification study, and every 5 years for a major classification study. Usually, shipping companies try to carry out with classification societies only the main 5-year studies, especially for their new vessels. This is possible because the specifications required for new vessels require a much higher standard of construction than was previously done. In any merchant shipping company, dry dock maintenance is very important to ensure that vessels are seaworthy and ready to perform the required operations. This can only be guaranteed if effective maintenance planning and management is achieved. In the current situation, dry docking maintenance is conducted based on 2 factors: previous dry docked maintenance, and due date for the Classification Society survey. However, other factors must also be considered to optimize the dry docking maintenance of ships, including factors such as the demand of a ship's operations and dockyard availability. As underlined above, the availability of vessels is paramount for commercial shipping companies. The corporate risk management strategy is based on this availability, and therefore unplanned or long-term maintenance operations are likely to have a significant negative impact on revenue and profitability. Therefore, maintenance in the dry dock must be optimally scheduled. This could be achieved by applying a mathematical approach to identify the best possible solution. To do this, Kuwait Oil Tanker Company, KOTC, uses a binary linear programming model. COT Fleet Dry Docking Maintenance Scheduling Model. The programming of the mathematical model for the optimization of dry dock maintenance for COT was developed at the University of Manchester. The example of a scheduling was conducted using data obtained from the COT fleet, which consists of 24 vessels and includes 3 different types of tankers: T1 crude oil tankers, T2 product oil tankers, T3 gas tankers. With each type having 2 different classes, and a planning horizon of 60 months. The mathematical technique used is a mixed integer programming (MIP) model to formulate the relationship between the variables and solve the resultant scheduling problem. The results of the case study are presented in the table. The Gantt chart visually presents the programming performed. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.